So, welcome everybody. It's my great pleasure to have our next speaker, Bastian Käfer from RWTH Aachen University. And he will talk about a Möbius invariant energy for sets of arbitrary dimension and codimension. Please.
Okay, so hello everyone, and thanks to the organizers for this nice online seminar and the opportunity to give this talk. And as Armin already said, I want to speak about a Möbius invariant energy for sets of arbitrary dimension and codimension. And this is actually a joint work with Heiko von der Mosel, who's also from Aachen. And so I want to show you some energy functionals which are invariant under Möbius transformation, which are basically combinations of translation, rotation, scaling, or inversion at the sphere. And after that, I will focus on one specific energy, and we will see some consequences we can obtain if this energy is finite. Okay, so let's start. So before I go to these higher dimensional energies, I want to introduce the Möbius energy for curves, which was defined by O'Hara, and then we will see some of the attempts that are made to get such an energy for higher dimensional sets. And after that, I go to the specific energy here, and we will see what happens if this energy value for a set is finite. And in the end, I will shortly show some of the ideas to prove the main theorem. Okay. So let's start with the one-dimensional case. The Möbius energy is actually one of the most famous knot energies. And if you're not too familiar with knots, just assume gamma to be some closed curve, which is defined on the unit interval into R3. And this curve has closed, Lipschitz continuous, and parameterized by arc length, which is given just by this condition here. And to obtain a knot, we also have to assume that this curve is injective, but we can define the energy for all these curves here. And then the energy is just the double integral over 1 over the Euclidean distance of 2 points squared minus 1 over the intrinsic distance squared. So I have to explain what this intrinsic distance here means. Therefore, we just take the closed curve gamma, have then 2 points on this curve here, gamma of s and gamma of t, and then of course on this here is just the Euclidean distance, and the intrinsic distance is the length of the shorter arc, which connects both points. So in this example here, it should be the lower part, so this red one. And of course, the intrinsic distance is always bigger or at least equal to the Euclidean distance. So we get that this energy is always non-negative. And this energy is also studied by many people. So there are many results. Just let me state a few of them. So I think interesting is that Friedman, he and Wang proved that this energy is invariant under Möbius transformation. And this is, of course, the reason why we call it Möbius energy. And they also used this to show the existence of minimizing knots if we restrict the energy to prime knot classes. So prime knots are just knots that cannot be decomposed into two non-trivial knots. So that's this here. And then we have minimizers for these special classes of knots. Okay, and O'Hara himself showed that the energy is self-repulsive, which means if we have a sequence of knots or sequence of injective closed curves, which converge toward a curve with self-intersections, then this energy here should explode. And by explode, I mean that the energy value goes to infinity. Okay, but there can also happen some strange things. So this pull-tight phenomenon can occur. So I think we have seen this already a few weeks ago. we can leave a knot class just by pulling the knotted part of the curve tight. So we converge towards some knot with which is in another knot class, and this energy doesn't punish this. Okay, but that's not too important for this talk. So we have some results for knot theory, or some curves, and of course we want to get some equivalent of this energy for higher dimensional sets. So the plan now is to define such an energy, and the problem is that we cannot do this with the formula we have already seen, so it's very hard to use this. But luckily, there is another interpretation of this formula. So Doyle and Trum used or showed that the energy can be written as this double integral over 1 minus the cosine of an angle which depends on s and t over the Euclidean distance of these points here squared plus some constant 4. So this 4 seems a bit surprising in the first moment, but this here is actually the right formula for the Möbius energy of the curve gamma. And okay, we have to look at this angle here. How is this defined? Therefore, we need the same curve as before. Then we can, or we have a tangent line at the point gamma of s here, and we can sorry, we can construct a sphere which is tangential at this red line here at the point gamma of s, and also contains the point gamma of t. So it looks like this, and we call it the tangent point sphere of s and t. Okay, and we can do the same for the second point and get another sphere here. And okay, just let me take it to the right. So we have both spheres here. And then the angle alpha is just defined by this intersection here. So we take the tangent planes to the spheres, and the angle is just this, the angle of these two lines. And of course, because of the symmetry, we also can take any other intersection points of these spheres. So for one dimension here, we have this. And okay, then we can write the Möbius energy as this new integral. And this can be done for any dimension. So we can do the same for m-dimensional surfaces in Rn. The only thing that changed is that we do not have some tangent lines. We have m-dimensional tangent planes. And also these spheres here, we can construct them, but they are m-dimensional now. But okay, so we can do this. And this is exactly what Kusner and Sullivan did. And they said that we take sigma, which is an m-dimensional submanifold of Rn, then we can define an energy as a double integral over a set. And then we integrate a function f, which depends on exactly this angle, over the Euclidean distance of p minus q to the power of 2m, so 2 times the dimension. And they even gave some examples how we should choose this function f. So mainly they focused on this one, so 1 minus cosine of this angle to the power of m. But they also mentioned this sine to the power of k, where it's not really clear how we should choose this power k here. So in my opinion, it should be 2m, so 2 times the dimension, or at least bigger than the dimension to be a good energy. And then the only thing we have to think about is how do we define angles for m-dimensional planes? So we do not have a single value. but we can choose different directions. So we have m planes, then we have m different dimensions, and for each direction we can get one angle, and they are called principal angles. And Kusner and Sullivan just use the combined angle with this formula here. So their cosine of the angle is equal to the product of these m angles in the cosine. Okay, and they also stated some results for such energies. They said if this function f is non-negative, then of course the whole energy is not negative. That's not too hard to see, but more importantly is the second result. So they said if f depends only on one of these principal angles, or formula depending only on these principal angles, then the whole energy is Möbius invariant. And this property is what we want to get. Okay, so as this is a nice example for Möbius invariant energy. Okay, of course there are also some other Möbius invariant energies. For example, Oakley and Sardou gave an energy, but they used some second order information. So I think some integral with means curvature or something like that. But we stayed with the idea of Kusner and Sullivan and made some minor changes to this. And we said that sigma don't have to be a submanifold, but an m-dimensional admissible set. So yeah, I will describe this later here, what admissible set means. But because since we don't have a submanifold anymore, we have to define an additional map P, which maps points of sigma into the Kusnerian, which is for me just a set of m-dimensional planes in Rn. And then we use these planes here to define the angle for the integrand, because in general we don't have any tangent planes. And then we can easily attach a new plane to each point P and Q, construct these spheres in the same way as before, and then we get a new angle, okay? And then we have to decide which function we want to use for our energy, and we used this specific function here, which is sometimes also called the gap between planes, and it's just defined as the operator norm of the orthogonal projection on the first plane minus the projection on the second plane, and then the operator norm is just a supremum over all unit vectors. Okay, and in our case, this first plane P is just the red plane P of P here, and the second plane Q is this dashed plane here. So it's the plane P of Q just attached to P here in this case. Okay, so now we have to show that this energy is actually Möbius invariant, but this is very easy because we can prove that the gap between these planes here is actually the sine of one of these principal angles, and this here is actually the biggest principal angle. So this is the sine of the biggest angle that can occur between these two planes. Okay, and then Kusner and Sullivan already said if it only depends on this angle here, then the energy is Möbius invariant. Okay, and now we can even see that there are some relations between our energy and the energies that were mentioned by Kusner and Sullivan. And for this, we have three different cases. The first one is if this k we use as a power for our integrand is between m and strictly less than 2 times the dimension, then we see that this sign energy and our gap energy here are equivalent, so we can estimate one by the other. And whenever I write this symbol here, I mean that this energy is less or equal than a constant times this energy here. So these here are equivalent, but they are more singular than this cosine energy here. So we didn't get an estimate in the other direction here. Okay, and if we choose k to be equal to 2 times m, then this is kind of a special case because all three energies are equivalent. This is nice. We have to keep that in mind. And the last case is if the power k is bigger than 2 times the dimension, then the sign energy and our energy are still equivalent, but they are not as singular as the cosine energy. Okay, so we have many inequalities here. Just keep in mind that all three energies are somehow related, and in this case here, k equal to 2 times the dimension is somehow special. So that's what we keep in mind. Okay, and now we can go to some of the consequences we get if the energy value is finite for this our energy. And I want to start with the main theorem. We have basically 3 conditions, and I will describe them in detail just in a moment. I want to give you some idea of this statement first. And okay, we have an m-dimensional set, so m is between 2 and n, and the power for the integrand is at least the dimension. And then we suppose that sigma is uniformly covered by alpha Lipschitz graph for a very small constant. Okay, so just think about that like sigma is the union of many Lipschitz graphs. And this Lipschitz graphs have a very small constant. This is this condition, and then we need that these planes we use to define the energy respects this covering. Okay, and this means that all these planes here are tangential to some parts of sigma whenever it's possible. Okay, so we take nice planes for energy, and then the last condition is that sigma has controlled self-intersection, which is actually hard to describe. So, and it's also some technical reason, and we want to okay. So just a moment. So I have a question. So what does uniformly mean? I think it is covering here. So we have these graph patches here, and I want that on all compact set we have graph patches of a uniform size. So we don't have some sequences of graph patches that get smaller and smaller and smaller. Okay, and that holds for all compact sets or compact subsets of sigma. Okay, and yes, so the third condition here is technical, and actually we try to get rid of this at the moment, but for the moment we just have to assume this. And it says that in each neighborhood of sigma, there has to be some points where we do not have transversal self-intersections of sigma. So we'll see that just in a moment, but this is some condition for the intersections. And then we can say, if the energy of sigma is finite, then for all compact subsets K, there's a radius such that sigma can be written as a single graph patch. So we have some submanifold condition here, and this function up here is just one of the function we started with in this Lipschitz covering here. So it's Lipschitz continuous, and this gave us some representation, and we say that there is no other graph patch in this local neighborhood of P. Okay, so let me describe these three conditions in detail. The first one is
so what is relation to the please return to the yeah, for this formula they are not K. So what is K?
So K is a compact subset of sigma, and we say that this R here is uniformly for all P and K. So we have a uniform size of the graph patch.
Okay, so this condition is this K. Okay, thanks.
Okay, so yeah, so we can go to the uniform covering of sigma, and it says that for all compact subset of sigma, there's the radius. So we have this uniform size here, such that for all points in this compact set, there exist two planes, so an n-dimensional plane, and a Lipschitz continuous function defined on this plane into its perpendicular, such that the graph of up is contained in sigma. So we only have here some inclusion here, and the Lipschitz constant of up is bounded within this neighborhood of P. So a neighborhood of 0 should be here, so sorry. Okay, and this means that if we know that P is contained in sigma, we already know that there's a whole graph patch that's also contained in sigma. So this blue one here. But what we not know is that, or if there are any other parts of sigma, so it may look like this. There are some other graph patches contained in the neighborhood of P, and there could be even infinitely many graph patches here. But what we know is that there is no isolated point. So if here's some point of sigma, then we know there's this graph patch which corresponds to this point, and this has to be in sigma 2. Okay, so and yeah, if you do not like this kind of definition, just assume this example here. If we choose M to be a compact m-dimensional C1 manifold, and it is mapped into Rn by an immersion, then this sets here satisfies this condition. This is because we can cover these sets by C1 graphs, and because of this C1, we can choose the scale of the graph patch small enough such that the Lipschitz constant is bounded by any alpha, and because of the compactness of M, we can do this also uniformly. So we get such an R here. Okay, and this is an important example for this class of sets. Okay, so we go to the next condition, and we say that these maps we use for the energy respects this covering of sigma if for almost all Q, this map P, this plane P of Q is tangential to at least one of the graph patches. So if Q is somewhere here, P of Q has to be tangential to the blue graph patch. If this Q is an intersection point, so here it has to be tangential to the blue one or one of the red ones, which doesn't make much of a difference here. So yeah, it's almost the same, but for points here where we intersect with an high angle, then it's really matters if this plane is tangential to the red one or to the blue one. And of course, we only used Lipschitz continuity. So there are some points in this image here or here where we do not have tangent planes at all. So we can assume this only for almost all Q in our sigma, but this is okay since we only want to integrate over the set. Okay, so this is what this respects the covering means. Sorry. And for the last condition, we say that for all compact K, so subsets of sigma again, there exists some constant and the radius such that if we take one graph patch, so let's say the blue one again, and then we take an arbitrary point of this graph patch, so maybe here, and in the neighborhood of this point, there has to be enough points where this map P behaves well. And by behaving well, I mean that this angle condition here holds true. So the angle between the domain of UP and this plane through the point for the integration has to be bounded by a constant times our Lipschitz constant alpha. And we need enough points to do this. I mean that this measure here, measure of the sets of all points who satisfies this, has to be bigger than a constant times the radius to the m. Okay, so let's see where this property can fail. Just assume that this here is the plane PP. Then if we take some points here, then we know already that this map P has to be tangential to the blue graph patch. And because of the Lipschitz continuity, we already know that the angles to tangent lines to or tangent planes to these points here, and the domain of UP has to be small. So this is okay. And so we have to look at intersection points. If we take this intersection points here, where we have this tangential or almost tangential intersection, then we still have no problem because we have this threshold of 3 alpha, and this should be okay in this situation if the tangent plane of the red one or the tangent plane of the blue one are both okay. But we could get problems if we choose this intersection point here and choose the plane P or this plane P of S to be tangential to the red graph patch here. Then this angle condition here could fail, but we only want that this measure condition here holds. So there are enough points in the neighborhood of this intersection such that this here is still true, so we have no problem. And we can see that this only can be wrong or fails if we have infinitely many intersections of sigma with itself, and all these intersections has to be transversal, so they must have a high angle. And also we need that these intersection points have positive measure. And at the moment we try to get rid of this condition. So we want to prove that holds for all nice sets. So let's say for all compact sets. And well, it's really hard to do this. But what we can do is, if we take this example from before, so our set is just the image of a compact C1 manifold, which is immersed into Rn, then this condition here almost is almost true. And the main reason for this is that we can include the intersection points of 2 C1 graphs into lower dimensional submanifolds. And then because of this compactness of M, we only have to consider finitely many different graph patches. And then we can see that the set where this condition here is wrong is measure of this set is 0. So for these sets here, everything is okay. But for our more general class, we have still problems. Okay, so we have, I have explained all 3 conditions. And if they hold, then we get that finite energy implies that sigma is locally, can locally be given by a single graph patch. And there's no other graph patch contained in the neighborhood of P. And as I already mentioned, is that for immersed C1 manifolds, the first condition and the third condition are always true. So we get a simple implication which states if we are in this situation, so we have compact M-dimensional C1 manifold, which is mapped by an immersion into Rn, and these planes we use for the energy respects this covering, so it's almost everywhere tangential. Then we have that finite energy for the image implies that our set is a C1 submanifold, so it's locally given by graph patches of C1 functions. Okay, and the reason for this is that we showed in our main theorem that we get a graph representation by one of the graphs of the covering we start with. So if we start with C1 graphs, then in the end we obviously get still C1 graphs for the representation. And with the same argument, we get that we can replace every C1 here with an CK. So so it's the same argument. And more interesting is that we can also change the energy. So we can replace this gap energy here with one of the 2 energies we've seen in the beginning. So if the energy of the sine energy or this cosine energy is finite, we can find a k such that this energy also is finite, and then we can use our result. Okay, there's a question. Right, so these are different case, sorry. I should have used some different letters. Okay, so yeah, I want to mention some current results from O'Hara. So he uploaded a paper on the archive this month, and he said that this cosine energy here is self-repulsive if we restrict it to C2 submanifolds with bounded curvature. So we have these C2 submanifolds, and they somehow converge towards some surface with self-intersections. Then the energy value of this here goes to infinity. And this is related with our results, since we showed that if the energy is finite, then there cannot be any self-intersections, and O'Hara showed that if we converge towards some self-intersections, then the energy should go to infinity. So I want to mention this result here. It's some new and stated this month, so you can read this. And okay, the next question should be if we get any additional regularity if the energy is finite. So that would be quite nice, but sadly we cannot answer this, so this is still open, but I think that this should be possible. But what we can say in the moment is that if U is not only Lipschitz, but has some additional fractional Sobolev regularity here, and we can write sigma as the graph locally of this U, then we can estimate this corresponding part of the energy just by a constant times the semi-norm of the derivative of u. So this semi-norm here is just part of this norm of this fractional solar space here. And of course, if we have some compact submanifold with this regularity here, then the energy of this sigma should be finite. Okay. So, okay. Before I go to the, just one question. So yes, in this case, k, the k is the same, so that is important. So this k here and here and here are the same. Okay, and yeah, before I go to the proof of the main theorem, I would just want to shortly mention a relation of this energy to some energy that is not Möbius invariant. So for everyone who knows it, it's not very surprising, but this is the tangent point energy. So we just take the double integral over 1 over the tangent point radius to the power of k. And this radius here is just the radius of these 3 years we used in the beginning to define our angle. And because I don't have enough time, I only want to say that these energies here are related. So this and this Möbius energy. And this whole technique we used to prove the main theorem was actually intended to confirm a conjecture of Strzelecki and von der Mosel, and they said that immersed C1 manifolds with finite tangent point energy in the scale invariant case. So if we choose k to be equals to 2 times the dimension of M, and if this energy is finite, then this set has to be embedded. So it's a C1 submanifold of Rn, and we actually proved this much earlier than we do for the Möbius energy. So we proved that if M is compact and mapped by an immersion into Rn, then this finite energy here implies that it is embedded, so that the image is we actually showed that the image is a C1 submanifold. And here we also can replace this whole C1 part with our 3 conditions of the main theorem. So I can do the same, and also the proof works the same. Okay, and if we have this result here, we can apply some results of Simon Blatt, which states that this set should be should have some additional Sobolev regularity here. So, and yeah, okay, so this. But now let me go to the proof of the main theorem, or the a short sketch of the proof. So to remind you, we have just these 3 conditions and want to prove that sigma is given by a single graph patch. Okay, so and the first step, and I think the hardest one, is that we want to bound the beta numbers of this set. And beta numbers are just a way to describe how good a set can be approximated by planes. And it's defined as 1 over R, sorry, the supremum over all points in the neighborhood of P, and then we take the distance of these points to a plane through P. Okay, and we want to prove that for all small radius, we can bound this by a constant times alpha. Okay, and we also want to do this uniformly on all compact sets. Okay, so we take again our graph patch UP. We know that this has to exist, and all these points here are okay. So the distance of points in the graph patch to the plane are very small, so we can estimate these by the Lipschitz constant. Okay, so the only way that this condition here can fail is if there exists another point Q in the neighborhood of P. Okay, and now the plan is to show that this situation here leads to some constant value of energy. So, and by constant I mean it does not depend on the radius, so on this radius of this neighborhood of P. And then if there is no constant such that this condition of the beta numbers are true for all smaller scales, then we can define a sequence of such situations, and each of these situations gave some constant value of energy, and then the energy of the whole set sigma has to be at least the sum over these small energy portions, and then the energy has to be infinity, because we sum over infinity many times the same constant. Okay, so the only thing we have to do is to show that this situation here gives us some constant part of some constant value of energy. And therefore we have to distinguish a few cases. So the first one is, what if these plane through P and the plane through Q are almost the same, so they have a small angle. Then we know that here is some graph patch at Q, so this is because of our first condition. And then you can imagine that comparing this part here with this part here doesn't give us much energy. So we can construct these spheres and see that these spheres tangential at some points here and containing points here, and the other way around are almost the same, and therefore these energy, these points doesn't give us much energy. And what we can do is we compare this graph patch here with points who are much farther away from this the projection point of Q, so somewhere here and here, and then we get in fact some energy value, and this energy value doesn't depend on the scale. So so that is what we want to do. We compare this part here of the graph patch of UP with this here, and that gave us the high energy. And the same we can do if these planes are different. So if there's a high angle between P of Q, so the plane through Q and the plane through P, then we can also draw some spheres and look where we can get the highest angles. And the best thing that should be done is comparing this graph patch at Q with points that are near to P's. That should be the best, but sadly this doesn't work for us. So there are some technical problems here, and we have to come up with something else. And the solution was to do this at a much smaller scale. So we compared this graph patch at Q with whatever is contained in the graph patch of UP and is much farther outside. So somewhere here and here. And then in this situation, we get our constant energy value by comparing these sets. So for the first integral of our energy, we use these points here, and the second one we use these. So that's okay, and then we can go through every case and see that in the end, if this condition here failed for all scales, then we get infinitely high energy. So this is in contradiction to our condition of finite energy, and therefore this beta condition has to hold for at least all small radii. Okay, and that was I think the hardest part of the proof. The next step is to to bound theta numbers. So theta numbers are kind of similar to beta numbers, but we use the Hausdorff distance to measure this distance to the plane. So we compare some part of sigma to this neighborhood in the plane. And because of this bounding of the beta numbers, we already know that the set sigma is somewhere contained within this dashed line, so somewhere here. And the only thing we have to do now is to compare or to estimate the distance of points in the plane to parts of sigma. So we take just some point here in the plane, and we already know that there is this graph patch, this blue graph patch, so we can estimate this distance to sigma by the distance to this graph patch. And again, because of this Lipschitz constant of this graph, we know that this here is also bounded by constant times the Lipschitz constant alpha, and therefore we already have this condition here, and we already have this uniformly on our compact subsets of sigma. And this actually has a name, so it's called Reifenberg-flat, so with respect to this constant. And this is a really nice condition, which I've studied a lot while my master's thesis and still using it. And this gave us, or this gives some topological or geometrical results. And this is, this is key for our result. And okay, so we have this condition, but at the moment we do not know if there is still some parts of sigma in this neighborhood here. So we have to exclude this. Okay, so it's just the definition of this Reifenberg-flatness, and basically we have to there has to exist a radius on all compact sets such that we have for each plane, each point P, we have a plane such that these theta numbers are bounded, and that is exactly the situation we are in now. And or in fact we are even better, because we know that these planes we use to approximate our set sigma are independent of this radius r. So we have proven this theta condition for fixed planes here, and then we can use this for all small radius already. And this allows us to apply the following lemma, which says, okay, here's it, which says that if we have a Reifenberg-flat set and we take 2 points, P and Q, which are not too far from each other, and we can bound the angles between these approximating planes here for scale r and rho, and this angle plus delta is strictly less than 1, then we know that in the neighborhood of P, there is no other point that projects onto the same point as Q. So this is this condition here. So there are no 2 points projection on the same. And in our consideration, this means that we can take some point on the blue graph patch here, and we know, applying this lemma, that there is no other point in this neighborhood of P that projects on the same point. So this red point here cannot exist. And we can do this for all points on this blue graph patch. So we all actually know that it should look like this. So there is no other part of sigma that can be in this neighborhood here. And then we already have proven our main theory. So that's this. And okay, we have chosen alpha to be very, very small. And the main reason for this is that we have to guarantee that this constant for the Reifenberg-flatness is smaller than 1/2. So that's the reason therefore. Okay, and now I am done with my talk. So thank you for your time and your attention. And I would be happy to answer your questions.
All right, thank you very much. Are there any questions, preferably via the microphone?
Thank you very much for your very inspiring talk. What can you say in general on the global minimizers for more or less closed objects? So will there always be spheres, or does this depend for certain choices of M and K?
So I think the minimizers should be spheres, yes. So for these sets, so can go. So we mean for touched analytically here, or
yep, for all these families that.
Okay, so for all these families, if we take a sphere, so a single sphere, then all these angles here should be 0, and then the whole energy is 0. So that should be the minimizer. Well, so here, yeah, this slide.
Okay, and the same reasoning works for the other families as well.
At least for these 3 energies I've here. Yeah. So then, if you take a sphere and construct these tangent plane spheres, are always the same, and then the angle of these planes is 0.
Okay, thank you very much.
Any other question? Remarks, comments?
Yes, well, thanks for the very nice talk. So I have one question about these admissible sets. Do you have any hope to reduce the assumptions you have to make in the future? Maybe something like a varifold without boundary might be enough? I have no idea.
Maybe, so I don't know.
Do you have counterexamples? Any examples that your conditions are actually necessary?
So I think the first 2 are necessary, yeah. But the third one, I don't know. So we try to get rid of this, but yeah, it feels like this should be true for all sets, but we cannot prove it at the moment.
Okay, thank you.
So there's another question in the chat.
Okay. Okay, so okay, something's happening here. So actually, I don't know if they are. So we don't use some analytical continuation. So we just used some geometric inequalities and just use different parts of sigma to integrate, and then we get this result.
Dimitri, does that answer your question? So Dimitri wrote like another line. Can you define the energy through analytic continuation?
I haven't tried that one, so I really don't know if we can do this, but yeah, sorry, I don't know.
All right, further questions, voice or in the chat? So that seems not to be the case. So let's thank the speaker again.